So, am I audible? Okay. Today I will be talking about a variant of noisy channel. We call it elastic noisy channels. And I will explain how we can construct secure multi-party computation protocols efficiently over these more realistic noisy channel models. This is joint work with Darshita Khurana and Amit Sahai. And in the talk, first I will introduce what elastic noisy channels are, and then I will explain how we build secure multi-party computation protocols efficiently over them. And the crucial part which underlies the privacy arguments of our construction is this new information theoretic phenomena called capacity inversion. So I will explain this using some examples. We won't be going into strict mathematical formulations. So to begin, let me just go ahead and explain what elastic noisy channels are, in fact. So suppose we have cell phones and we want to use them as weak transmitters and receivers to perform secure multi-party computation. A transmitter might be transmitting a sequence of bits, and a receiver, since it is a weak receiver, might not receive each bit perfectly. In this case, say a third of the bits are erased. But the receiver could turn adversarial. This receiver could go ahead and install a larger antenna. This increases the reliability of reception at his end. So now the bits are erased only with probability 1/6. So in fact, what happens is that some bits which were erased earlier are not erased anymore. Now, given this additional advantage that this receiver has, can we still perform secure multi-party computation because the sender doesn't know whether it is talking to an honest receiver or an adversarial receiver? This can be formalized easily as an elastic version of a binary erasure channel. In a binary erasure channel, the sender sends a bit B, and it is delivered with probability 1/3 if the receiver is honest. Otherwise, the bit is erased. And if the receiver is adversarial, then the bit is erased only with probability 1/6. Note that the sender doesn't know whether the bit was dropped or not, and the receiver doesn't know the input bit if it receives the erased symbol. Now, given this model of an elastic binary erasure channel, our task is to construct oblivious transfer using such elastic versions of binary erasure channel. I want to emphasize that we only want to construct one. I will only show you how to construct one OT, because given this qualitative result, we know how to convert it into a quantitative result. That is, we can construct large number of OTs. So we are just interested in the qualitative result. So such a protocol will have the following property. For correctness, if the sender has private inputs x0 and x1, and the receiver has private input bit C, then we expect the receiver to obtain the secret x sub C. The privacy of such a protocol should insist that the sender should not be able to find out the the private input of the sender, that is the bit C. On the other hand, a adversarial receiver should not be able to find out the other secret, that is x1 minus C. Now let me go ahead and give you the protocol which implements one oblivious transfer from elastic versions of binary erasure channel. On the left side, we have the sender. On the right side, we have the sender, and on the left side, we have the receiver. The sender has private input bits x0 and x1, and the receiver has private input bit C. To explain the protocol, I will assume that the choice bit C is 0. First of all, the sender sends a large number of bits through the erasure channel, and the receiver receives a few of them, and some of these bits are erased. In this example, in this case, for example, a third of the bits are erased. The black bits represent the bits which have been erased. Now, the receiver partitions the set of the indices 0, 1 to 5 into two parts, such that the first set of indices comprises of bits of indices corresponding to bits it has received. Let's go over this again. The receiver randomly partitions the set 0 to 5 into two equal subsets such that the first subset comprises of indices corresponding to bits which were all received. Now, if C was 1, we would have swapped these two sets. The receiver sends these two indices, the set of indices 1, 0, 3 and 3, 2, 4, 2, 4, 5 to the sender. The sender sees that the first set comprises of indices 1, 0, 3, so its secret shares the secret x0 as b1 plus b0 plus b3 and a bit r0. Next, it sees the second set as 2, 4, 5, so its secret shares x1 as b2 plus b4 plus b5 plus the bit r1. And now the sender sends these two bits r0, r1 to the receiver. Now we can see that it is easy for the receiver to obtain its secret because she already knows b1, b2, b3 and knows r0, so it can easily recover the secret x sub c. Now, this protocol, for example, it is easy to see that it is correct, but why is it private? So let us try to argue about the receiver privacy. Note that the sender, the only additional information that the sender sees is these two sets. Over the randomness of the erasure channel and over the internal randomness of the receiver, these two partitions are just a random partition of the set into two equal sets of the set 0, 1 to 5.
So this is just a naive question. Why don't you just use an error correcting code?
Error correcting code does not. Error correcting code removes errors. It cannot ensure privacy. This is, in some sense, an error correcting code. It's like it is secret sharing plus an error correcting code.
If you use just a usual Oblivious Transfer protocol and then use error correcting code on top of it?
There is no Oblivious Transfer protocol. We are trying to build it.
That assumption.
It's an unconditional result, information theoretic, in presence of, forget about multilinear maps.
Can you go back to the correctness? What happens if I get one black point from the first set and one from the second?
So receiver has constructed these two sets, right?
But it's arbitrary.
Yeah, but he has constructed, because she wanted to obtain C0, she has constructed this set that it knows all the secrets.
But
If I wanted C1, I would have constructed this set with all indices such that it knows everything.
Can you state clearly what is the assumption about the channel?
The channel is that there is a sender and a receiver, and it has two properties, alpha and beta, for example. Alpha is the probability of erasure when the receiver is honest, and beta is some smaller probability of erasure when the receiver is adversarial. For example, if you have an erasure channel, if I'm honest, I will receive with probability 33%. If I'm adversarial, I receive with probability much higher than 33%. I receive the bit identically.
And then when you want an oblivious transfer, you want two properties. When they're honest, it works, and when they're dishonest, it's secure?
It's always secure, yeah. Yeah.
You're also assuming independent erasure. So that is
Yes, IID. Is this clear? So the protocol is clear, right?
Even if the receiver isn't cheating though, and just probabilistically they end up getting more.
Yeah, but chain of bound it is low, right? So let me go ahead with the security proof. Is it fine, or there are more questions? Yes.
One question that I would really like to is related to the elasticity. I mean, if it's not elastic but you don't know P.
The exact, so you know the bound of the P, and that suffices.
Right, no, but my point is the problem of elastic things the same as the problem that you have when there is a P but you just don't know it, or are these...
No, it is slightly different as well. Like, so you can adversely see. In our case, there is a strategy of reaching the higher resolution. Like, suppose you know that the channel characteristic lies in the range alpha to beta. In our case, it's a reality that an adversary can install an antenna which gives it beta. In your case, it might not even be possible. That the reality might be far from beta.
What did you say?
Chernoff, it's enough that you didn't get 1 bit.
Yes, by Chernoff you will not get 1 bit. So let me go ahead with the security proof. So now let me argue the sender security. In this case, the receiver is adversarial. So recall that the adversarial receiver can increase the reliability of the communication, and therefore.
So just to interrupt for a second, I think maybe there are some more questions for the speakers. So I'm hearing them. So.
Yeah. If you have questions, yes. This is the most complicated protocol we'll ever see in this talk. So let's go ahead. Yeah. Yeah. So 6 is long. Yeah. We'll replace it by the security parameter number of bits.
Yehuda, you have a question?
Sorry. So we just I'm assuming that you know, so the honest receiver must get enough non-erasers to actually.
Yes. I will formally state that result in the next slide. So. For the sender security, recall that, so let me go over the sender security again. In the case of sender security, the adversarial sender can make the channel more reliable. So some of these erasures can actually be received by this receiver. And now it has some bits which have been erased. For example, in this case, 1/6 of the bits have been erased. To argue security, let's track one of the bits which has been erased. In this case, the bit indexed 5 comes in this set, and I'm going to claim that this secret, the second secret, is perfectly hidden because this bit B5 is perfectly hidden. Because the receiver did not receive the bit B5, so the receiver cannot recreate or extract the other bit X1 minus C. So it's a perfect security, if such a bit exists. Is this argument clear?
Maybe you're going to talk about it late, but I remember there was a work, maybe it was by you, which can see that kind of a more challenging setting of adversarial errors in an interval.
Here also, in this case also, like if it is in an interval, adversarial error, it's also fine. If you introduce adversarial errors.
Not erasures, errors.
Yes, we'll come to errors. We'll come to errors. So, now, yeah.
Some of the bits are missing in the first bits that you are sending, the first chunk. Because your channel is randomized.
Yes.
So you send, here you send constant number of bits, but assume you have to...
I'm sending security parameter number of bits. It's not constant. It's security parameter number of bits. And
sure that there is some...
yes, but it's, yeah. Okay. So now that we are fine with the security of this protocol, let me go ahead and state our formal theorem. So if we have an alpha beta, one more question. Should I go back? Okay.
No, but did you prove the security against the malicious sign?
Yes, it was. I said that these are a random partition.
No, but if I'm the sender, I can on purpose give. I can decide where to.
It's semi-honest. Semi-honest. Okay. As I'm stating it, it is semi-honest, but our results can be made adversarial. Like against its UC adversaries also, it is complete. Like this construction works, a modification of it. But I won't be going it. It's easier just to motivate using the semi-honest.
But when you talk about semi-honest, who controls the probability between 1/3?
It's a third party. It's a universe introducing random noise, let's say, first of all. The channel is a third person.
So for each message, somebody has to choose a number between 1/3 and 1/6. How is this number chosen for each message?
No. So it's a channel.
There is like one number
Yeah,
forever.
yeah. If the receiver becomes adversarial, he chooses a channel which is better.
Well, but the more powerful mode, for each tick, he can choose a
Yeah.
probability between 1/3 and 1/6.
No.
The adversarial will always want the less. It's easy to prove. Yeah, you can look at that.
Yeah. Should we move ahead or still? Okay. So actually what we have proven is that if you have an alpha beta erasure channel, That is, alpha is the probability of erasure when the receiver is honest, and beta is the probability of erasure when the receiver is adversarial. Then, if alpha and beta are less than half, then we can construct oblivious transfer from such an elastic version of binary erasure channel. Here we crucially use that at least half of the symbols arrive. Okay? Now, in fact, we can actually increase this number from half to 1 using techniques from error correcting codes. So I'm not going to go into the details of that. The summary of this slide is that for any non-trivial choices of alpha beta, we can construct secure multiparty computation over such variants of such elastic variants of binary erasure channel. Yes, it can be upgraded to UC secure protocols. It's a UC secure, like.
Questions?
Just to recap, you need the upper bound on alpha to make sure that
at least half.
Proceeds,
yes.
And you need the lower bound on beta for.
At least one is missed. Then you can go all the way to half by repeat. The obvious thing is to repeat, but you can do more efficient things.
Are you going to explain how this relates to this model of unfair noise in channels?
Yes. Yes. So the model of unfair noisy channel, in that both the receiver and the sender can change the channel characteristic. In this, only the receiver can change. They had strong negative impossibility results because, according to me, I do not believe that that's a very nice model. And they have very strong impossibility results. In our case, I will show you that very strong possibility feasibility results are possible.
So does the efficiency of the protocol depend on beta and alpha?
Yes, the efficiency and the number of OTs that you will be able to extract depends on that.
Right, so I mean, if beta was negligibly small?
Negligibly small is useless. It's a trivial channel because it's a channel which always reliably delivers a bit is cryptographically infertile.
So you never get that the protocol gets exponential complexity?
Yes, in that, think of all alpha betas as constants. Because beta is the probability of erasure for the adversary. So adversary wants more and more information.
But even if it gets less, the security still holds.
Yes, but I'm saying that my protocol security.
There's a typo.
Where?
It should be beta less than or equal to alpha. Yeah.
Beta. Okay. It's easy case. Everyone knows that.
Not even less than or equal to.
Right. Right. Yeah. The non-trivial.
Forgetting things.
Yeah.
I'm good at that, actually.
It's no longer an elastic channel. I mean,
So let's go ahead and try to see why exactly our protocol worked. I gave you a protocol, I gave you proof, but why exactly it's worked? To do that, let me introduce the notion of capacity of a channel. Intuitively, it means how much information an output symbol carries about its input symbol. So suppose we have a channel which always reliably forwards its input bit. We say that it has capacity 1. If we have a channel which always erases the bit that the sender provides, then we say that it has capacity 0. Now, let me show you how we can draw a graph representing binary erasure channels. Recall that when the sender sends the input bit 0, the receiver either receives 0 or the symbol bot. And if the sender sends input bit 1, then the receiver either receives 1 or bot. This is a graphical representation of a binary erasure channel. Now, we can similarly represent the graph of a message forwarding channel. And we can also represent graphically the picture of a message erasing channel. Note that a binary erasure channel is a convex linear combination of these two sub-channels. And the capacity of this channel, recall, was 1, and capacity of this channel was 0, and consequently, the capacity of this channel is 1 minus epsilon. So, till this point, I want to understand what we have done. We have drawn a picture of binary erasure channel, and then we have decomposed it into two subchannels with very different capacities. Note that if the receiver is honest, the maximum subchannel capacity is 1. of the two channels, the maximum sub-channel capacity is 1. If the receiver is adversarial, in that case, the average channel capacity, that is the average sub-channel capacity, is 1 minus epsilon, where epsilon is beta. So the real reason why our protocol actually remains private and is a secure implementation of Oblivious Transfer is because there exists a gap between these two numbers. I want to emphasize that we are not comparing the highest sub-channel capacity with the highest adversarial sub-channel capacity. We are not comparing the average with the average. We are comparing the highest with the average. This is extremely crucial. So, given this abstraction, let us try to use this knowledge on more channels, like binary symmetric channel. In a binary symmetric channel, a sender sends a bit B, and with certain probability, the bit is delivered or it is flipped. If the receiver is honest, then the bit is flipped with probability 1/3, and if the receiver is adversarial, then it is flipped only with probability 1/6. Note that in this case, both sender and receiver do not know whether the input bit was flipped or not. Now, an elastic version of a binary symmetric channel can be parameterized by two parameters, alpha and beta, where alpha is the probability that the input bit is flipped when the receiver is honest, and beta is the probability that the input bit is flipped when receiver is adversarial. The question we ask is, for which values of parameters, alpha and beta, we can indeed securely implement Oblivious Transfer. Okay, let's try to use whatever we learned. Let's try to graphically represent binary symmetric channel. That is simple. We have input bit 0, then we get 0 or 1. If you have input bit 1, then you get 1 and 0. But there is no obvious way of decomposing this graph into subgraphs or sub-channels such that they have very different channel capacities. Here, it is, so here our main idea is that instead of encoding the message 0 with the bit 0 and encoding a message 1 with the bit 1, we use this following trick. We are going to encode the message 0 with, say, 2 repetitions of 0, and the message 1 using 1, 1. We are going to send these 2 bits through two independent binary symmetric channel instances. Now, the receiver receives one of these 4 output symbols. Note that the top 2 symbols could be interpreted as output of a different binary symmetric channel, which takes 0, 0 as input or 1, 1 as input. And the bottom 2 symbols could be interpreted as output of a binary symmetric channel, which takes 0, 0 or 1, 1 as input. In fact, this is just a message erasure channel. It also has the probability that this channel has lower capacity than the channel that we started off with, and that channel has a lower capacity than the channel on the top. What have we achieved? At least we have achieved our first step. We have been able to break binary symmetric channel into sub-channels such that the sub-channels have very different capacities. Okay, but why stop at 2, right? Like, we have a good thing going. So why stop at encodings of length 2? We can go 3, 4, and further. So yes, we can do that. We can encode 0 with 0, 0, 0, and we can encode 1 as 1, 1, 1, and pass it through 3 repetitions of binary, 3 independent instances of binary symmetric channel. The receiver receives one of these 8 symbols, and one can show that the top 2 could be interpreted as outcome of a particular binary symmetric channel, and the bottom 6 symbols could also be interpreted as output of one particular binary symmetric channel. So again, we have expressed our original channel as a convex linear combination of different channels such that they have very different channel capacities. Okay, the first point is done. We have been able to decompose the channels, but have we ensured that the maximum honest subchannel capacity surpasses the average adversarial subchannel capacity? Let me explain that using a particular example. Suppose alpha is 1/3 and beta is 1/6. For this particular value, let me show how we can achieve that goal. I will do it using pictures. So in this picture, the y-axis is capacity. The blue rectangles are subchannels corresponding to adversarial receiver case. The green rectangles are capacities of subchannels corresponding to honest receiver case. The x-axis will be probability that a certain subchannel actually is used to process the input. So when we start, we have only one subchannel. And the honest maximum subchannel capacity is significantly lower than the average adversarial capacity. If you use encodings of length 2, then both these quantities increase, but believe me, these two actually get closer to each other. What are these two quantities? Let's again look at them. This is the maximum capacity in the honest receiver case, and this is the average capacity in the adversarial receiver case. So we keep using encodings of greater and greater length. These two keep getting closer and closer. And at 6, we are nearly there. And if we use encodings of length 7, surprisingly now, what we have is that the maximum honest subchannel capacity surpasses the average adversarial subchannel capacity. At this point, we say that capacity inversion has taken place, and the encoding which achieves it is known as a capacity inverting encoding. So if we have a capacity inverting encoding, then we can go ahead and construct an oblivious transfer from such an elastic noisy channel. Okay, what we have shown is that for this particular alpha and beta, oblivious transfer can be constructed using encodings of length 7. But for which values of alpha and beta does there exist capacity inverting encodings? Alternately, for which values of alpha and beta does capacity inversion occur? Okay, let me go ahead and again prove it using some pictures. So this is a graph which will represent the set of feasible parameters. The y-axis will represent the flip probability in the honest receiver case, and the x-axis will represent the flip probability of the adversarial receiver case. If you use encodings of length 1, we never have capacity inversion. If we use encodings of length 2, then we gain a small range of feasible parameters. Okay, let me explain how to interpret this graph. Suppose the adversarial flip probability is 0.1, then all these values of alpha experience capacity inversion. Now, if we are using encodings of greater length, more and more parameters start experiencing capacity inversion. This space keeps on increasing until it hits a limiting curve. I call it limit beta curve. Let me give an example of what kind of parameters our protocols can achieve. So suppose there exists a binary symmetric channel in which the honest receiver has alpha equal to 30%, and adversarial receiver has beta equal to 5%. Then our protocol constructs oblivious transfer from such versions of elastic binary symmetric channel. An alternate way of interpreting it is that suppose the best receiver in the market is 95% accurate. Then we can design protocols which implement oblivious transfer, even assuming that the honest party uses a weak receiver which is only 70% accurate. So what we have proven is that when alpha and beta is bounded by limit beta, then there exists a secure protocol for oblivious transfer from these elastic variants of binary symmetric channel. The question here is, what exactly did we gain? How much did we improve the prior state of the art? For last 25 years, there have been lots of work on constructing oblivious transfer from noisy channels and weak variants of it. Using these techniques in our setting, the only feasibility parameters known for our case was this small minuscule fraction denoted in this green. Let me give an example. Suppose the best antenna in the market is 95% accurate, then these protocols need to assume that the honest party uses an antenna which is 94% accurate. There is only 1% gap. It's not at all satisfactory. So our work adds this huge range of parameters, and we can even assume that the honest party has a 70% accurate receiver. Can we go beyond this? It's not known. I conjecture, yes, indeed we can. And mostly because I believe so, and there are no impossibility results known. To conclude, I just want to say that this notion of capacity inversion is extremely fundamental property of noisy channels, and I think it can be leveraged in general information theoretic cryptographic protocol design. It's clear actually that there are some very low-hanging fruits as well that we can try to attack. Like we can try to increase the parameter space for what we have done in our work, or we can also try considering other variants of noisy channels like AWGN channels. The last problem is something which I like the most. I want to quantitatively find out what is the maximum limit of efficiency that we can get. Given n copies of a particular noisy channel, how many copies of OTs that I can implement? Think about it. It's just an analog of the problem of capacity in error correcting codes that we are posing for for MPCs. And even this fundamental quantity is not known. With that thought, I would like to conclude my talk. Thanks.
We're a little over in time. Let's look at a couple of questions. What is the length of the encoding in terms of alpha and beta?
It's a constant. For every constant alpha beta, there exists a constant for which a constant encoding.
Have a formula?
We don't have a closed form formula. We have an algorithm which finds it in logarithmic time. Like whatever the encoding length is, we can find it in logarithmic time.
One obvious thing to try in order to get better parameters is to look at the softer target, like a defective oblivious transfer, where the defect in correctness is smaller than that of privacy, and then maybe the honest user can use not just the max, but also the things below.
Actually, there is a separate project where we are exploring these things. In the project of combiners and extractors for OT, we are considering these kind of problems there. Yes?
Or a comment perhaps that if you compare to earlier work on fan noisy channels, you should, in fairness, I think also remember that those protocols had to cope with the fact that also the sender could modify the channel.
Yes.
There may be a reason why it's harder to guess.
No, yes, I mentioned this, that in unfair channels, both receiver and and the sender can change the channel characteristic, and that causes existence of strong impossibility results.
Yeah. So that's also, I mean, do you have a comment on this? I'm thinking that if the motivation for considering elastic channels is that maybe the sender buys, maybe the receiver buys a bigger antenna. One could also contemplate maybe the receiver sends a stronger signal.
But that is detectable, right? Like you can detect that, oh, you have sent a larger signal, and I've said I'm not going to participate in the protocol anymore. So we didn't want that model actually. But by the way, we conjectured that our techniques are going to be also useful for the unfair channel technique. Like the impossibility result is subsumed by encodings of length 2 in our setting. I think we conjecture that it's going to be useful for that setting as well.
That would be really interesting actually. Because
yes.
Unknown area.
Yes.
Yeah, I think maybe we'll stop the discussion here and go to the break. Maybe we can take this offline if that's all right. Thanks, Maji.